Test, test.
I'm gonna leave that mic on. Um, that just means when you're ready to talk, just pick it up. Perfect. Oh yes, that. Believe me, they've been staring at my face all day because they keep joining Teams calls for all of these. But seriously, thank you for doing
decided to leave. Wow. I haven't started threatening you yet, you know, right? So,
Would you rather us focus on our project or the presentation?
well, you see, in my experience, if you kind of, in my experience, if you're not productive, it's time to take the break. You're not gonna go far away. So, in any case, whatever you do, you should take a break because then you'll have this huge amount of time to finish the whole project. And if you will push yourself, it's just not gonna do good for you, you know.
You got us. She said we're not productive anyways. Plot twist. Why not sit here? What time was it supposed to start? Yeah. I'm sitting right here. I was we can see all I was looking at that. We showed it to our teammate as well. Yeah, in the background it's there and she just left. Yeah. Yeah, it was out there when she left. Like she said like the art of not quitting and she quit. So very ironic, but it's
Oh gosh, you are hilarious. Jeez.
you have a great audience.
I bet. Okay, we'll see. Well, can you hear me now? Right. That's probably more for people who are joining us all the way from another part of Cincinnati. Hey, how's it going? I'm not gonna be threatening you with anything, but right. Okay, well, but I mean, I don't want to be forcing you to be here. If you want, I mean, like, well, okay. That all works. That all works. Perfect. Okay, let's just get into it. Well, thank you so much for people who are not quitting today, because today is a conversation about how not to quit, and it's amazing to see so many people here. Although some people are quitting throughout the night, which is fine. Some people are not quitting throughout the night. That's all right. You know, when you get the good dinner, it just doesn't really make any sense right after. So let's hop into it. So today, my goal is not to give you a technical talk about the research or about the technologies I used to work. Today, my goal is to introduce you to a new mindset, because throughout my life, I used to work with problems where people say it's impossible to solve those problems. And I always had this idea in my mind that there is no such an impossible problem to solve. But then when you define something as possible to solve, how do you exactly limit the scope? So throughout my time, I used to work with a couple of different labs around the country, and now I'm pursuing my PhD in computer science and electrical engineering here in Cincinnati. And I hope you guys enjoy it. If at some point you want to ask a question, go ahead. It's pretty nice that we have this sort of smallish, still not small to be honest, but a pretty interactive audience. So we'll see. Oop, perfect. It seems like the clicker is quitting. Right, so here's our agenda. We're gonna go all the way of the definition, and we're gonna go all over the terms that I'm gonna be using today. Then I will also explain a little bit, I guess just introduce how we can measure the technological success from the lower boundary when we say that how not to go lower and how to perform at a pretty successful level. And I will also measure at the higher level where we can say, well, you cannot call that task as impossible. And then at the end, I will just guide you through a couple of my life work experience, what I've done in the past, and I put a bunch of research examples throughout the presentation. So hopefully you will have fun. So a little bit about the introduction. I'm telling you that thing is quitting. So about the introduction. So in the past, I used to work in a couple of different research labs. So I worked mainly in the area of machine learning, computer vision, artificial intelligence. My background comes up from University of California at Davis. And for the last 2-3 years, I used to work with projects affiliated with NASA, Stanford, MIT, and pretty much the whole conversation I will have today based on all the projects I line up throughout my past years of experience. So let's dive right in. First of all, let's define the limit. Before we do so, I would like to encourage to keep one of the questions in mind. What is the definition of quitting? And especially, there are a lot of books, for example, if you run the company, if you run the startup, some people might say, well, we are running low on money, the runway is not far away, maybe we should sell the company, or maybe we should give up on a specific technology. Or if somebody's working on a project and you feel that it doesn't work, should it be even going towards that direction? Keep that question in mind, because you never know, and I will try probably to clarify a little bit how we can build a whole systematic approach towards technological development. So, quick definitions. So, what is quitting in general? What do you guys think? How would we define quitting in general? Okay, okay, stop trying, sure. But is it a valid point to say you better to stop trying? How do you measure this decision-making phase when you actually decide that you should quit?
I personally feel like failure and quitting are basically correlated. So basically, when you stop trying and you lose your hope. But if you are trying for something, but you have already quit virtually, so
Sure.
that's basically what I believe.
Okay, what's up? Those two ideas, they're actually very easily combinable, and I love it. Yeah, as we can see here, that's pretty much what we're saying there about quitting in general, and then constraints. So that's a whole idea how we can line up quitting and constraints at the same time, because usually the compounds are pretty much four main compounds. So we have quitting, which is, as you said, the definition. And then we go all the way to strategic stop and pivot, which is write down another idea behind you from the person. And then we have constraints that help us. Yeah, that's funny. Yeah, well, yeah, I guess we're having those jokes all the time. Yeah, and then we have constraints all the way to justify the quitting and the limits. It's fine. We're just gonna keep on. Yeah. Yeah. No. I know you're not gonna quit. It's fine. Right. So one of the cool practices to try with your ideas. I know that team in particular is using Moscow. I will talk about Moscow a little bit later on, which is must have, should have, could have, and would have. That is a prioritization framework. How you can build priorities on your ideas and make sure you're able to implement the whole project throughout the time. But what is also interesting, we also have RAM decision trees. So the whole idea is to measure in a cycle your realistic expectations. So you try to combine reversibility. So what is happening in your technology? So what's going to happen if you're going to stop it? You're also trying to balance at the same time the evidence. So are this data is getting sort of, am I getting tricked by the data? Or maybe is it a falsification of the results? Is it a biased experiment? And especially in the research lab, that's the case. And lastly is marginal learning. So the idea is to balance those things and figure out if evidence is yes, which means we are doing a really good thing here. And we also know that M, which is marginal learning, is low. So why not to keep going? Why not to keep working towards that specific direction? And taking on the next step further, and you probably guys realized that is as a whole different framework comparable to Moscow. It's also about requirements, but it still helps you to clear up the path of the priorities. So here's an example of constraints. Let's take it another level. Let's say E is yes, and the marginal learning is we can keep moving to the next step. So what we're gonna say, we have a lot of, how would I say that? I should even probably correct myself, because every single task, we can shuffle it in a flexible way. So instead of saying that specific constraint is must-have or recommended, we can say there is a priority ranking on each of the constraints. And the question is, the higher the priority, we don't touch that constraint because it's must-have. And then if it's a lower priority, maybe we first want to solve the specific problem and then build on top of that constraint. So for example, if we want to go to space, I will talk about space in a while, but if we want to go to moon, right, the constraint is mass of the lunar lander. And then you can say, oh, well, hey, let's just put not 4K camera, 8K camera, it's gonna be heavier, but we don't have the rocket to actually get to the moon. So who cares what kind of camera you're gonna put on the lander if you're not gonna make it there anyway? So that's why here we have a couple of examples of constraints. There could be physical, there could be algorithmical, there could be coding constraints, pragmatics constraint, financials, pretty much self-explanatory, and the most important, architectural constraints. So what do we do with that next? Next, I would like to use an example from NASA-style mission cycle. So in general, how NASA develops missions is actually pushing through every single checkpoint and milestone. But there is a big difference between the milestone and the gate. We will talk about gates in a second. So milestone is a point in time when we actually just gonna achieve that specific goal, confirm, test, validate, and move to the next step. Meanwhile, the gate is a decision-making point where you say, we're good to go or we're not good to go. So those particular things, the checkpoints, they're marked in yellow and they're marked in triangles, but technically every single mission development stage is the go, not go decision-making sort of unit. And here, a couple of examples of how far you can go. Pretty much every single checkpoint answers a specific question. Every single gate asks the go, not go. So by the end of every single time, you get a confirmation from a lot of scientists. So for example, for one of the projects, when the team I was part of, I think we moved all the way to CDR. And what is interesting is that those reports, they're humongous, because the idea is those previous slides that I showed you, we want to build on top of those things. And what is interesting, you start with high level, lower, 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 low level, and MCR is up to 20, 25 pages. PDR is all the way to 30, 50 pages. Our CDR was 260 pages. My team was 16 people. We've been validated by other 5, 6 people on another side, because you want to make sure you want to get this unbiased opinion. And the question you want to answer yourself, every single gate point is it worth doing? Am I on the right track? Because you don't want to be building the rocket and then say that's just a waste of time, money, and why would we do that? So now how could we learn from that experience? Well, we can approach systematically. Now, if we're going to move a little bit to the projects that you're all working here tonight, we want to make sure you are able to ask yourself the questions on the right, and you want to validate. And again, that's probably fine for the judging, and I would probably be satisfied as a judge too. But my main mission here is to build boundaries out of the box. So if you go further beyond, and I know you will all go further, you want to aim for the higher bar. If you start the company, because recently Cincinnati is right on the startup location here, and we also want to go all the way to the research, right? So that's the whole point. You don't want to be building this more or less average, right? You want to be aiming, I guess, for the stars. It's pretty ironic we're talking about space, and yeah, in plain English, you pretty much want to know if your acceleration and if your trajectory is actually getting you to the path of success. And if it's not, it's okay to pivot, but not quit yet, because we will talk about when exactly to quit, right? Yeah, apparently, yeah. First one? Well, yeah, I guess it's very subjective, but the whole point you define throughout all those gate points, what is X, Y, and N, right? So, which one again? Oh, the kill criteria. Yeah, yeah. I mean, it's pretty much if you want to be going further or not, but anyways, oh, okay. Yeah, yeah, yeah. Exactly, exactly. Yeah, totally. Exactly. Okay. Well, shall we move to the next chapter? Yeah, I think that it seems like that's what is happening actually. That's well, it's no, it's actually no, it's well, you see what is important about engineering is that oh, you seriously want to be doing that? I mean, you taking notes. I mean, I can do that. It's fine. Sure. I mean, it's yeah, definitely. Yeah, sure. Well, thank you. I mean, take a seat. It's gonna take some time. Like, yeah, yeah, sure, definitely. Well, thank you for doing that. Well, you know what is interesting about. I just want to take the opportunity to acknowledge what's happening. Like the clicker doesn't work, which is fine, right? But the idea is. The mindset that I'm trying to introduce here is that it doesn't matter how the technology works as long as we are responding in a correct way and we control our behavior, right? So, well, I can stay and complain like, oh, this goddamn clicker, right? But I mean, how would it help, right? So when we build those priorities, my responsibility and to make sure I know how to react. So in that particular case, why would I be complaining when I can just move on, right? So it's again, it's a pivot, that's a constraint. Well, now let's move to the scope, right? So now I introduced all those different terms. So now let's talk about different boundaries. Let's call them thresholds. So first of all, we're gonna say how to build for the future. And then we're gonna see how to build something that is reliable right now. Next slide, please. So a couple of examples from the history, and I do believe, I'm a big fan of history, and I do believe that history has a trend of repeating itself. Well, apparently it's sort of assumed that we would learn from history. I guess human beings are pretty complicated creatures, so once in a while we don't, once in a while we don't really. Yeah, well, I was just putting it, right? But that's a whole different story. All the way different story. So what I'm trying to say here, one of the key arguments is that to figure it out if the technology is ready. So let's say we passed all those tests with gates, checkpoints, milestones. We know what we're building. We have all those requirements. So now what's happening on the next stage? So we first want to start building the technology, not from the technology to the customer. We want to build it from a customer to technology. And here is one of the great examples is actually what happened with Microsoft at 2002, which is apparently they introduced a pretty cool tablet and people just weren't ready for that. Apparently, could be just general education, could be self-awareness and understanding that you actually need the tablet. Another aspect, financial, obviously. Thinking of the Concorde flying from the US to Europe, right? Also same financial problem. But now look at the United and NASA introducing the first supersonic flights. So now Apple introduces iPad in 2010 and ships it by the end of the year. And now guess who is actually succeeding in terms of tiny tablets, iPads, and phones? And it took another 5-6 years to equal up the equilibrium based on the research. So that is one of the examples how we can make sure that people are ready. On the next slide, actually, let's move to the next slide. We're gonna get back to space, and here's one of the shockers that I've experienced myself, how many years it actually takes to build the rocket engine. So RS-25, it is a competitor of the Russian engine, because American and Russian engines, they have a phenomenal performance. And back to the time of Soviet Union, there was also pretty much no competition for Russian space program pretty much. But right now what is happening is that NASA is very smart about the testing and production. So it takes almost 5 years to manufacture and produce one single engine. And then it will take another couple of years to validate it, test it, explode it a couple of times, push it to the limit on the lower boundary, upper boundary, then mix it with the current technology and put it on the top of SLS, which is pretty much a booster and first stage that is going to make us back to the moon. What is interesting about RS-25 is that imagine you are propulsion engineers at NASA. Actually, Marshall, that picture is taken at Alabama Marshall Flight Space Center. What is interesting is that imagine you want to fly to the moon, but you don't have a rocket. You don't have the way how to build a sustainable life environment. You don't have the way how to get oxygen for astronauts to go for 2 weeks. So how would you make sure that all the technologies, they're going to be aligned together, perfectly aligned? Every single point is well tested, but in 20 years. That's the whole problem. How can you guess, not I guess, I don't want to be using that word, but how you can forecast and predict the trend of the current technology, make sure that right now it's not going to be working, but in 20 years we would have the perfect environment to incorporate that engine to the SLS system, and we're going to get back to the moon. So, next slide. I guess one of the ways is actually learning and researching and trying to fail as many times as possible. Here's an example of Mars lander. And I want to get a bit of the transition why we're moving from the engines to the trajectory. What is interesting about Mars is that we would assume that every single planet is almost perfectly spherical. But what is interesting about Mars is that if you will take a look at the elevation map, you would see that apparently the South Pole seems to be higher than the North Pole by actually 10, 15 kilometers, 30 kilometers, even higher. So Mars is not as spherical as Earth or any other planet. So now, how would it affect our landing trajectory? So if you go to the North Pole or if you go to the middle lane, you have additional 20 kilometers to slow down. Now, if you go to South Pole, you don't have those kilometers. So the problem with space is not to get to the Mars. It's actually to slow down, not to crash on the surface. So now we're working on the mission, obviously, to get back to the moon and then go to Mars. But what is exciting is that if we don't have a new propulsion, you cannot get back to Mars. But then if we do have that propulsion, we don't have a rocket. So how can we build the rocket, propulsion, everything at the same time? And our Artemis mission goes all the way to 35, 36. So it's pretty much in 11 years at this point. So how do we make sure that all the technologies are going to line up somewhere there in the future in 11 years? And here's one of the examples. At my knowledge, the propulsion system was developed also at Marshall Flight Space Center, where people took almost a decade to figure it out how to slow down. And we finally did it. Next slide. Here's actually, I thought would be a cool idea to show the timeline, just so you understand the complexity of the project. Because Artemis 1 is one of the Artemis 2, 3, 4, 5, and even more. But what is interesting about that mission in particular is that every single checkpoint, it's not just a milestone. It's a whole project that will take you half a decade. And lining up your future is one of the most critical skills to develop, but at the same time, in my opinion, one of the most challenging accomplishments you can achieve as an engineer, to be able to predict the future. And maybe predict is not the best word to use, because it's sort of gamble and statistics, but in a way you want to have control over the technology, and you cannot just go ask for billions of dollars and build the rocket and say, well, trust me, we're going to get there. That's all about how you acknowledge the environment and is that technology actually will be ready on the span of the next 10, 20, 30, even 40 years. Next slide, please. Here's a cool GIF at bypass behind Earth, and what is pretty beautifully scary is that beautiful picture, but you don't get much of a signal at some point. Now we're taking technology even in the next level, because now it's not just the future, it's always autonomous robotics. And teaching the machine to behave in a certain way, especially right now in the age of machine learning, that's something that should ring the bell, because how do we know that all the machines will be behaving in a certain way throughout the time span the next 10, 15, 20 years? And that's the whole overview of Artemis mission at the time a year ago, just to give an introduction how complicated the mission in general. Next slide. So when we want to answer the question, will you be ready? Are you ready? Have you been ready in the past? You follow those certain patterns. You want to break every single checkpoint as lower as possible, at the sub-level, at the low level. And then if it's not doable or verifiable on a way of math or physics, conceptually, within hours, that's probably not small enough. You probably want to go lower and lower. Obviously, here's an example. If I'm going to say, well, let's talk about rocket science right now, probably I have not many chances actually succeeding in that task, right? Because it's a complicated topic. But what we can do, we can split it by physics aspect, math aspect, chemistry aspects, and then we can split math into calculus, and then calculus into variables. We can go lower, lower, lower until we hit this baseline and we know what we're talking about. So that is the whole point, to make sure you can measure every single term and every single concept you're working with. Next slide. So now we're going to go into the blockers. So blockers are usually on the lower boundary, and they're trying to connect the higher boundary. So, for example, you're working on blockers right now. And, I mean, he's locked in, but it's fine. But, no, I'm now he's freaked out. No, I'm just saying that, no, you don't need to be freaked out. Well, I'm just kidding. No, I'm just saying that you try to perform at a certain level, and there are things that slow you down because it's challenging. Let's learn a little bit about how to overcome those challenges and how to detect those challenges. Let's go to the next slide. So here's one of the examples. In the past, I worked on the new NASA technology report that was trying to improve the performance of some of the robots at the space station. And a couple of things you probably wouldn't really expect is that, yes, it's computer science and electronics, but then by the end of the day, you go to the operational, you go to seriously, I think operational system would be a really good example. You go to learn about how the code works, and that's a pretty old school code, which people try to update all the time. There are famous rules to write the code at NASA. But what is interesting is that if you don't have basics, and if you're not willing to be flexible and go down to the level of assembly and C in the age where it's pretty attractive to know Java and Python, yeah, what's up? Oh, I guess no questions. Yeah, it's fine. No, I just thought. Then it's a complication. That's a big problem. Another problem is that apparently space station goes all around the Earth, and it would be nice to talk to Earth once in a while, call your family, take pictures, take a selfie in front of United States all the way from the orbit, but it's not that simple. So when we send the signal back on Earth, we want to make sure the timing is perfect. So now you arrive at the project with an idea, oh, let's just fix something and improve it, and now you actually have to deal with a little bit lower level problems. And you most likely don't want to be dealing with those things, but it is how it is. It's been built that way, and you have to acknowledge it, and you have to move on, because that's one of the greatest skills the engineer can show, is actually open the mind and open the heart towards the technological advancement. Here is a pretty cool example of what could slow down that robot. Physical performance, memory performance, architectural constraint, financials, and you can always say, oh, let's just send a new robot all the way to the space station. Well, it's going to cost you a lot of money. Why not just to learn a language and write a good code? So that's a little bit about being smarter, how you treat in blockers. The next slide, please. Oh, that's funny. Almost, thank you. There you go. So, the loops. How we can know what are the constraints and how we can react on those constraints. So first of all, we can produce the minimum case. And we can see if we can actually negotiate the technological, not the technological, I guess the technology survey to make sure some of the technologies should be solid, some of the technologies, they could be flexible. So can we actually negotiate those terms? Well, obviously we can go all over the scope and we can build different tables, we can build the priorities. One of the examples would be isolation of figures and flags to make sure that we actually know the full scope of the constraints and of the full scope of the problems. And then we go to the hypothesis tables where we actually learn how to react on those things, how to test, how to detect the failures, the leakages, the corruption. And then we go all the way to the tests and to the final decision-making point where we actually want to know, well, for that particular technology, we've done the whole cycle. Should we look back because it wasn't enough? That's kind of what is happening right now in AI, because if you would see it goes trending up and down and we're getting back to the same beginning, but at the bigger level. That is what is important to remember. Let's move on to the next application. So summarizing, I was sitting on that table, on that figure, I should say, for a minute, and apparently you can actually summarize those things. If you would represent the scores for all your guiding questions, how to develop the technology, and how to rebalance the minimum threshold with the upper threshold, you can actually know at which place you stand in. And here's an example how you can do that. So it's pretty much the cluster problem between how we can continue, how we can pivot, how we can rescope again, and how we can quit. Because quitting and stopping is also important. But as you see, it doesn't take 50 or 100% of your decision-making capacity. It could take around 25, even less than 25%. Let's go to the next slide. So real-world results. A couple of cool projects and a couple of applications, how we can use the methodology I'm introducing here. Let's dive into the first slide. So one of the fun projects I've done back at UC Davis was was a collaboration of UC Davis Health. And the problem is, when you go to the operating room, there are a lot of instruments. And another problem is that somebody will be counting those instruments. And even worse, it's going to be happening almost 5-6 times within the span of 2-3 hours. It will take forever to count so many times, so many instruments. The checklists go all the way to 150, 200 instruments every 30 minutes, although it will be taking you 30 minutes to count those instruments. So somebody is actually performing the surgery and somebody non-stop counting instruments for 4 hours straight. Plus human mistake, errors, confirmational bias. Well, maybe we can be smart about it. So here's a comparison of the ideal world and real world. So how could we approach those constraints? Let's go to the next slide. Well, being smart about data, which is one of the, I guess you would agree, right? Instead of, no, you wouldn't agree, no. No, being, what is that? Okay, yeah, I mean, I know you told me about the project and the major, your major. So probably you do understand the actual problem. So Sure, but I mean, that's a perfect combination because, for example, my lab works all the time between the medical hospital and the computer science department. So, and I'm not saying because my health is not getting better, I'm just kidding. No, I've just been cracking joke with folks there that you should be sleeping well. Um, but yeah, but it's quite a detour because it seems like nobody will be sleeping tonight here. But let's get back to the slide. So the main idea, let's be smart about data. Let's apply all the principles that been introduced earlier into the real world application. So here we have a problem. In a surgical room, we want to count instruments. It should be extremely accurate. It should be fast, no delays, a pretty end-to-end pipeline right away. So how would we do that? Here's one of the examples of pre-processing, validation, testing, and then rotating images, exporting the masks of all those images based on the segmentation, binary tests, cosine similarities. So all those application and technological libraries, they pretty much gives you an opportunity to transfer image into the vector space and then do all the calculations in the vector space before you actually make the decision in real world. So now let's go to the last part of that pipeline, next slide. What is interesting is that then when you know what you're looking at, you can actually get back from the vector space all back to your picture and you can detect the instruments. So you can start with bounding boxes, then you can crop them, then you can apply another binary mask. Now you can crop the whole instrument at the second picture on the left. And then what is interesting, you can actually reverse that mask. So on the third picture, we have the forceps and we have the bulldogs that are pretty much holding the needle and they're holding the other instruments, or they have these openings in the skin, for example. They have the spiral inside, which is a pretty much, it has its sort of volume. It has its own space. It was pretty remarkable to being able to detect even the spiral shape at that level. That speaks for the accuracy that it's not about model, it's about the data. And that is another constraint because you want to make sure your data is clean rather than the model. And then the last picture is example of the confirmation and cross-validation that yes, indeed, we've detected the instruments. So now let's look at the final results. Let's move to the next slide. What is interesting here is that even within 20 epochs, the goal was to prove that you don't need a fancy GPU or TPU at Google Colab. You can actually try to run it at your CPU. And I think I ran that code on my laptop. And what is interesting, even without the cross-validation with the current YOLO model, just by fine-tuning the visual transformer from scratch, it would be possible to hit such an amazing accuracy for computer vision pipeline, but unfortunately not as good as we would expect in the medical industry. 95%, it's still 5% less than 100. So there is actually another paper that proves that we're approaching the stage where medical applications of AI is getting higher than the humans' correct decisions. But it's definitely not developed on the laptop. It takes almost a whole cycle of development throughout half a year or even more on the research from scratch. And then on the right side, you would probably see the examples of how exactly, nope, not yet. No, it's good. And on the right side, you would see the examples, how we would crop all those images to make sure we can actually see the exact shapes of those instruments. So let's go to the last example, navigation. I had so much fun building that project, and one of the reasons why is because I'm a big fan of, it's a bit of a detour though, I'm a big fan of quantum computing. And once at one of the conferences, I've heard this awesome idea of building the Dijkstra algorithm throughout the atomic grid. So if you would imagine the general Google Maps and the way how we know the tool, we have the graph and we have nodes and we have edges. So now for quantum computing, you would have the same thing. You would have the edges, which is pretty much the interaction between atoms. And those atoms would be your nodes in your graph or in your tree. So now what is interesting is that we cannot apply general calculus because now we have two variables. The edge could be changed and then the node could be changed. And what would we do when we have two variables and even more and more and more? We would ask help from multivariable calculus. So what happens at that level, at quantum computing, you can actually skip that part almost because those interactions are predictable and you can build sort of a more optimized Google Maps. But here wouldn't be the same idea of improving outdoor navigation and indoor navigation. And that's precisely what was been done is pretty much you have the whole indoor project being able to export the floor plans, and you have the whole other outdoor project to apply A*, which is the search algorithm for rebalancing edges and nodes, specifically applicable right now in the age of AI, because that's how the search works most of the times in the complex data structures. So now, the green dot is where we are right now. The blue dot is how we're going to leave the building we are right now. And then we have a connection on the outdoor map. And then we have the same connection between blue and green. How would we get into the building and get to the room where we want to get? So how do we do that? So on the next slide, I will show you the exact way how we can crop the floor plan. So here is an example. We will need to apply convolutional neural networks to crop the doors, because then we want to make sure we have white spaces between the walls, and we're going to run the A*. We've tried BFS, DFS, we've tried other search algorithms, but A* was the most optimal because that's a combination of your heuristic function and your shortest distance. That's why we want to make sure we're running from all the white pixels, not the black ones, because those are they're going to represent the doors, the walls, and in this life we cannot go just through the door and through the wall unless it's open. So we apply convolutional neural network and filters and preprocessing, Gaussian blurs, and rotations of the doors every 5 degrees to generate so many patterns of the door, and then we can overlay them together and we can crop that door. So here's an example of before door removal and after. Let's go to the next slide. So now, since we know how we can get out of the building, how do we line up the indoor with the outdoor? And that's a whole another question, because there is the open source library we've been working on is OSM, which is OpenStreetMap, and you can go and you can manually pretty much encode the whole campus. But we want to be smarter. We had almost 1,000 buildings at UC Davis, and you cannot really just go and encode all those 1,000 buildings. And then if you want to go to Cincinnati and then Boston, New York, so many schools, why would we be doing it manually when we can do automation? So we would run the shape detector, we will detect the exits, we will detect the entrances, the shapes of the walls, and then we will try to line the indoor with outdoor at the same time by slightly whatsoever rotating rotating the indoor convolutional network, not the convolutional network, sorry, rotating the indoor floor plan with the outdoor boundaries until it lines up perfectly. So on the next slide, here's the algorithm how it works. So you pretty much try to overlap the area by rotating left, right, and seeing by a couple of degrees what is the difference. And then if it's the smallest area, then that's your final angle, and your floor plan should fit exactly as the outdoor. Let's go to the next slide. And since it's challenge number 2, the problem is computation. And here's one of the examples. Right now, recently, literally 5 days ago, we just witnessed how the computational power and just being smart about algorithms can save you $1 billion, because DeepSeek recently released a new paper saying that instead of using the language tokens, we can transform it into the image and use visual tokens. Now, why would I be running my CNN all over again and waste my compute power, energy, and temperature when I can scale it down, do all my compute, and then scale it up back? But the problem is, what is the exact scale constant? And remember I mentioned that you keep rotating the floor plan until it fits. So that will show the highest confidence rate. And when it happens, you just quit. And that's how we know, because it's not going to get better. And in that particular case, that graph shows the exact moment and the exact scale when you should quit the training and resize it back to the real life constraint, and that's going to be your final output. Let's go to the next slide. The last challenge of that project was actually outdoor mapping. So we talked about indoor, we talked about outdoor, but the problem is our map was actually featuring something else. Crime rates, the blue poles to call 911. We also had the whole statistics and the whole mathematical model to predict weather patterns, wind, water, and we also were able pretty much to predict the traffic. What is interesting about UC Davis is that instead of walking, you bike. Imagine, you know how many people are in Cincinnati walking on campus, right? Imagine every single of that person biking. That's going to be a lot of bikers. At my knowledge, Davis in California is pretty, yeah. Well, the campus is, well, it's even worse. Yeah, so the question is, what about the constructions? And that was one of the features on the map. We were able to show that by predicting the traffic, you can actually avoid so many different slowdowns, because you use a star and you just rebalance the edge, because don't go there. Let's say the crime is high, the construction rate is high. Getting back to that picture, we had to construct the Markov chain, and we had to encode the whole campus using OpenStreetMap and apply computer vision to detect everything. Here's the main network in red, hand-driven as a scratch, and blue network as a secondary connector to the main network of the roads, where the bikers, cars, and pedestrians are pretty much going into the classes. And the problem is, how do we simulate the flow, the traffic? Because now we will have to use Markov chain to figure it out, actually, how the traffic correlates with the time of the day and how we can avoid traffic to make the way to the class faster. Let's go to the next slide. And it's a pretty interesting and fascinating solution. So we were able to combine the live data with constructing the Kalman filter. And it's quite ironic, and I should say I'm pretty proud saying that here at University of Cincinnati, because we have a professor who is teaching advanced computer networks here, and his advisor's advisors is actually Kalman. So the person who came up with that famous filter, we pretty much, we have faculty here who used to interact with advisors of advisor. By building the Kalman filter, we can predict the input into the network and the output out of the network. We can rebalance all the edges. We can combine it with the statistics of actual flow of bikers throughout the downtown Davis and campus of UC Davis. And then we can scale it, overfit it, and we can line it up perfectly with the trend of real life. And that's how we were able to build the simulation and maintain the precision of our Markov chain. Let's go to the next slide. And here's the result. You have the exit node, you have the entrance node, you create the Markov chain in the matrix form. Sometimes you can involve eigenvectors to save the computational power, and that's pretty much the whole solution. Let's go to the next slide. And finally, since you mentioned about the constructions and the concerns with crime rate, we being able to predict so many other different maps. The construction map, the crime rate map, the weather map. Here just 3 of the examples, how we can weight the graph throughout the nodes of the campus, which is pretty cool because you don't have to go every single time in person and count the roads and count the traffic. Yes, I think we've done a really great job of thinking in a smart way, because you can always say, let's just go and measure it manually. And it's fine to do at the beginning. But the whole idea here with technologies is being able to show that everything is about automation, everything is about pushing it out of the box, and everything, by the end of the day, it's not complaining about the clicker that doesn't really work, but but actually, yeah, but actually have a respond on those technological rather advancements, or rather some features and opportunities we can just improve for the future. Let's go to the next slide. That's it. On? Oh, yeah. I talk. No. Yeah, that's just a recap of all the calculations and all the traffic predictions. Yes. Yes, that's about it. Feel free to connect if you would like to. I've never, I've never seen people being so excited connecting on LinkedIn. Well, I'm, I'm thrilled. Thank you so much. Let's. Oh God. You see, that is what is interesting. What I sometimes get in my daily basis conversations is that try to build priorities not on exactly. Try to combine what you do to be at your goal destination with exactly what is the definition of your goal. And maybe after all, building all those cool projects and doing research and figuring out all the technologies, it's not really about trying to be as close as possible to technologies. It's actually about just doing what you like and being pretty passionate about what you love doing, and always trying to apply new science to the, I guess, the areas of our lives where we just need those technologies, desperately needs. And as long as you can find that need, trust me, there are so many other people and so many other labs and startups and companies who would need that mindset. So combining skill with the actual purpose, it is a very, very crucial, I guess, it's a milestone to achieve in the life. Because if you have more purpose but you don't know how to do that, it's hard to get to your final goal. But then on another side, if you don't have purpose but you know how to go somewhere, you might be going in the wrong direction. So if you can learn that by trying so many things, what you like, what you don't like, and failing and succeeding and failing again, you will get there. That's why that's why those aspects are extremely important if you want to be not just an engineer, but if you want to build a project from scratch, or if you want to do the cool research, even selling coffee, seriously, also. Even really selling coffee and being barista too. It's also the performance, it's also about passion, and it's also about your KPIs. If you're doing it pretty consistently and pretty fast, and you can serve so many people around you. It's kind of the same approach, isn't it? Yeah, I'm just saying it because I know there are a lot of people at 86 doing co-ops and doing volunteering work. Yeah, those people at the front row, and you would understand. Yeah. Yeah, totally. Sure. What's that? What is that? Yes. Yeah. I should. Yeah. You should sleep. Actually. Yes. I feel like. Yeah. Thank you so much, and do get some sleep. Do get some sleep. Definitely. I mean, it's cool to pull up throughout the whole night, but sleep is important. So.